afternoon, my name is Steve Seymour. I'm a Principal Solutions Architect at AWS. I'm one of our networking specialists. It's great to be back in Tel Aviv speaking again. It's been about a year since I've been here, and it's always great coming back. We have some great conversations about networking with many of you in the room here. So the purpose of this session is just to take you through some of the new features that we've launched in the last 12 months in terms of AWS networking, some of the new capabilities that we have, a couple of really quite cool, new, interesting features. So in terms of an agenda, this is how I've split the session up. We're going to spend a bit of time talking about account strategy and the way that that leads into some decisions you might make in terms of networking. We're going to take a look at one of the most common things we see customers do, which is publishing shared services and then making those available to other VPCs, other accounts, perhaps to other customers, other consumers of your services. Obviously, this is networking. We're going to have to talk about connectivity. That's a given. So a couple of topics around that. Network services, and what I mean by this are the services that support some of the other functions that you have in your VPC. And primarily here, we're going to spend a bit of time talking about DNS, so Route 53 resolver. And then finally, it's very common now for customers to be doing things in multiple AWS regions. So just a couple of pieces of information about our multi-region capabilities and the networking side of the services you can use here. So that's what we're going to try and get through in the next 40 minutes. Hopefully we can do that. There's a lot of interesting stuff in here. So let's start with account strategy. So what do I mean by this? Well, we tend to see two quite common patterns with customers in terms of what they do with their accounts and with their VPCs. So we either see larger, huge VPCs or accounts that have lots of infrastructure in them, but maybe just a single account. And within that, they would use IAM to control what you can actually do in that account. The other strategy we see is customers deploying lots and lots of very small VPCs, perhaps one per application, one per department, development, production, staging for each one of those, so lots and lots of very small VPCs. And the way these are typically managed is split kind of in two quite common ways. In those larger accounts, we typically see a lot of use of IAM, Identity and Access Management, using policies to control exactly what you can do, what you can't do, using very strict security groups to control who can access things inside that one large VPC. On the smaller side of things, if you're running these tiny VPCs with just a single application in them, what we then see is lots of automation. So the infrastructure is pretty much the same every single time. It's a cookie cutter approach, so we take an automated way of just deploying lots and lots of VPCs. You can do things like standardize on how you do connectivity, so VPN and Direct Connect. You need to automate that because you're going to be putting out lots and lots of these small VPCs. So this is how we tend to see things split, using policy and IAM or using kind of automation around the infrastructure and the networking. So some of the questions that you have to ask yourself when you're thinking about what model am I going to be using, and there is no right or wrong answer here. It's going to depend on your particular situation, your application. First of all, what are the different relationships between all of these components? So between the different accounts, between the different VPCs, do they actually trust each other? Are they within the same organization? So you're quite happy for traffic to flow between all of these components. Is the fact that all of these individual networks exist only because you've done this in separate accounts? And previously, we required you to have a VPC in each of those accounts to do it. So you have lots and lots of individual networks, but do you actually really need them? Do you want lots of VPCs? Security and networking, it's quite common for those two functions in an organization to be owned by a totally separate team to the one that is actually building the application. So actually, do the development teams really care that much about having to think about their network design, meeting all the individual security requirements that we have? And then finally, from a compliance perspective, are there different requirements for each of these accounts that you have? Do they need to be set up in a different way to meet some perhaps guidelines or local regulation? These are the kind of questions that might lead you to then make a decision about, do I go for a large VPC and put everyone in it, or do I create lots of small VPCs? You also might want to segment things inside your VPC and within your accounts. So we've talked about IAM, Identity and Access Management, lets you have users, groups, you can have roles. Using those, you can then be very fine-grained about what those individual users are able to do. So you can then set kind of a baseline for that. You can say the standard setup in a VPC requires users to be set up in a particular way. You can use security groups to allow whitelisted access into particular applications. So that's kind of the IAM security group side of things. In the VPC itself, you can then configure your networking to actually also enforce some of this. So does your application need to face the internet? So are you going to have public subnets, private subnets, perhaps use route tables to manage that? This is another way we see customers configuring their VPC. If we're going with one large VPC and we're going to put all of our applications inside it, we might go for this middle design here, where we have different subnets created for each application, multiple availability zones, great. We use network ACLs then to actually protect the flow of traffic between components and deny certain traffic flows. And then finally, we can get to a point where we say, let's just put each application in its own VPC. That's also acceptable as well. So I've given you kind of lots and lots of options there, but actually, wouldn't it be great if we could do all of those things, kind of both design patterns in one go? And that's where VPC Sharing came in. So this is something that we launched at re:Invent last year, as with many of the features I'm going to be talking about. And VPC Sharing allows you to create a VPC within one account, and then enable it to be used by many others. So here what we've done is we've taken the networking capability, so let's say we have a network engineering team. They're experts in networking. They know how to design a VPC, to lay out the subnets in a way that matches the standard organizational expectations. And then they're going to provide that oversight for the network. But the development engineers, they're the ones who are actually building the applications here. They don't want to have to think about the network at all. All they want to do is know, where do I launch my instances? Where do I identify the subnets that my Lambda functions are going to be using? So what we've done here is separated out that responsibility. But that also gives you a really nice side effect, that the network engineers are now the ones responsible for all the connectivity back to the data center, back to the on-premises network. And that's all shared by everyone that is using this VPC. So as it says at the bottom of the screen here, VPC Sharing easily enables you to share your VPC between different AWS accounts. So you can now have your own application team in their own account, tracked for their own billing, but launching into one big shared VPC. So let's take a look at how this might work. This is the infrastructure account, perhaps the networking team's account. We've got an application which we know is going to have to be available over the internet. So we're going to call that an external application. Like many external applications, it has a web component, so maybe just a web server, but also a back-end component, something that we want to keep private, something inside the VPC that never needs to be visible to the internet. We also have an internal application. This is perhaps a line of business type application, something that is only going to be available to the inside of your network, connected from the on-premises environment. So here are our two application examples. We're going to create a VPC. It's going to be 10.0/16. The networking team has taken care of this. In that VPC, they want to have standard subnets for everyone to use. So they're going to create two public subnets and two private subnets. This is a very common design. Each of those subnets in different availability zones, so one public and private per availability zone. This VPC is going to have an internet gateway because one of our requirements is our application is accessible from the internet. But also, it's going to have a virtual private gateway to provide access back to an on-premises network, so a VPN connection or maybe Direct Connect. We're going to configure the route tables in this VPC in the way that you'd expect. So for the public subnets, we're going to have a route table that says use the internet gateway, and for the private subnets, a route table that says let's use the virtual private gateway. This is where the interesting piece happens. We use something called RAM, Resource Access Manager, to now identify and share the subnets. So we're going to create two resource shares. We're going to create a public subnet resource share and a private subnet resource share. We're going to choose which of these subnets are associated with each of those shares, and then we're going to make those available. So in this case, we're sharing both public and private for our external application. It needs to be able to launch its web servers into those public subnets and launch its back-end servers into the private subnets. However, our internal application team, they don't ever need to publish anything to the internet. So their resource share, the one that they're using, only gives them access to the private subnets. So that's where they now launch their EC2 instances. Now, those external and internal applications are actually all being deployed inside their own accounts,
but actually they're being launched inside this shared VPC. So what do you see? If you're the owner of one of those applications, what is it you can actually see in terms of launching them? Well, you just see the subnets. You don't actually see anything else. So these subnets just look like they exist inside your account. So from the perspective of the external application, it sees all 4 subnets, and it can launch an EC2 instance into each one of them. From the perspective of the internal application, it only sees the private subnets. It doesn't even know that the public subnets exist. So that's kind of the power of Resource Access Manager and what you can do with VPC sharing. So you can still take that VPC and apply some of the other controls that we talked about before. So network ACLs. Let's say this is now a VPC with these 2 applications in, but they shouldn't be able to communicate with each other. Well, that's fine. We can configure the network ACLs as the networking team to block that traffic flow between different subnets. So it's a separation of duties here. Network access control, subnets, route tables, internet gateways, that's all the responsibility of the networking team. The individual EC2 instances, well, that's down to the team that actually built the application. So this is an example of what you might configure for the network ACL. It's denying traffic flow between 2 of the subnets. So I've mentioned that this gives you separation of duties. This means that you have that difference in responsibility between networking and the application owners. But the other thing it gives you is actually the ability to make the most of the resources in your VPC. This means that you can use all of the address space that you provisioned for that VPC. And in fact, you now might make it really quite huge because you're going to have multiple tenants running inside your VPC. It also allows you to separate out the 2 different responsibilities, separate out the networking component from the accounts that actually have the applications inside them. So where do you start with this? How do you decide what this is going to look like? Well, there's a couple of things to consider. So first of all, from a security perspective, keeping things simple is best. So if you can do this in a single VPC and you can easily identify the applications and the accounts that are going to be using it, fantastic. Do it in a single VPC. If you would actually like really strong isolation, so you want this application, it doesn't need to be able to talk to this application, put them in 2 different VPCs. That's a very strong isolation there. If you have lots of VPCs and you do need them to communicate with each other or perhaps with an on-premises environment, I talked about the fact that you might create a VPN connection in a shared VPC and everyone can use it. Well, what if you've got lots of VPCs? Well, I'm going to talk a bit more about Transit Gateway later on, but that gives you a method to be able to connect many VPCs to a single VPN connection. One of the things to think about if you're going down that path and wanting to connect lots of components together, lots of VPCs using Transit Gateway, is Transit Gateway has a lot of capabilities. It uses route tables inside the Transit Gateway to isolate these different environments and maintain routing to behave in the way that you want it to. So VPCs being able to reach on premises, but not being able to talk to each other is one design that I'm going to show you later on. So if we've got a VPC, we've got all of our services inside it, that's one design. But what if we actually want to share some services between VPCs? So really there are 2 things to talk about here. One of them is Transit Gateway, that way of connecting lots of VPCs together. It can enable you to do any-to-any connectivity, so all VPCs can talk to all other VPCs at a pure networking level. Everything could reach everything else. It's highly scalable. So Transit Gateway is built into the infrastructure of VPC, and therefore, in terms of scale, we're talking about thousands of VPCs. The way Transit Gateway is priced is based on attachments to the Transit Gateway. So each time you attach a VPC, there's a charge associated with that. The other perspective is to look at something called AWS PrivateLink. Now, PrivateLink has been around for just over a year or so now. And what this does is it very specifically enables one-to-many connectivity. I have a service that I want to present and make available to all of my other VPCs. It might be a logging service. It might be a proxy or something like that. And I just want to publish that service and make it available to all of my other VPCs. Again, it's highly scalable. It's built into the infrastructure of VPC. It uses network load balancer behind the scenes to then spread the traffic across some back-end instances. One of the really cool things that it lets you do is manage overlapping IP address space. So all of the VPCs that are consuming a service via PrivateLink, they could all be using exactly the same CIDR range for their VPC. Behind the scenes, we take care of that for you. So let's talk about the cool thing that is Transit Gateway. So Transit Gateway launched at reInvent last year. I was lucky enough to present the session on the launch of it. If you're interested in learning more about exactly how to configure Transit Gateway, go and take a look at Net 331 from reInvent. It's on YouTube and it's on SlideShare. But I did just want to take you through some of the concepts. Now, I can't really talk about Transit Gateway with at least not referencing Transit VPC. Transit VPC is a design pattern that we published a few years ago for using EC2 instances to connect multiple VPCs together. And there's probably a fair few of you that have used the Transit VPC design. It uses VPN connections and virtual private gateways to create a hub and spoke type setup, connecting everything together. But it does have some challenges. If all you want to use it for is connecting those VPCs, it's pretty simple. But the minute you want to customize it, you now need to manage the Lambda functions behind the scenes. And in terms of scale, it's still a pair of EC2 instances that you're routing your traffic through. So it gets hard to scale. It's hard to manage this environment. It's also quite difficult to then segment the routing within it. If you only want these 3 VPCs to talk to this one, but your VPN connection to be shared between them all, that's quite a complex configuration in the Transit VPC pattern. So we took the feedback that we heard from customers around Transit VPC and the pattern that we published, and we decided that we were going to build a native feature to do this, and that's what Transit Gateway actually is. So when I say it's a native service, it's built into the fabric of VPC. It's the same infrastructure that's delivering the packets between your individual EC2 instances. That's where Transit Gateway exists. It uses elastic network interfaces in each of the availability zones that you're using for your VPC. So what that means is some of those bandwidth challenges on the Transit VPC design, they don't exist with Transit Gateway. It scales horizontally behind the scenes. It uses a technology that we call hyperplane. It's the same technology that exists behind NAT Gateway, behind EFS endpoints, and a few other services. And finally, it does give you that capability to have flexible segmentation. And what I mean by that is that ability to have separate route tables and identify different behaviors for different VPCs and different VPN connections. So there's a lot to take in there. Let's look at some of the detail behind Transit Gateway. So first of all, Transit Gateway is a regional object. You create one, it exists within a region, and it can connect various resources inside that region. It has huge scale. And when I say huge scale, I'm talking about thousands of VPCs. So you want to connect 4,000 VPCs together? No problem. Transit Gateway will do that for you. It has this concept of routing domains, this ability to identify what needs to communicate with each other by creating the route tables. And I'm going to show you that in a moment. And then finally, it has integration options with partners. So if you have a partner, or you are a partner that perhaps has a solution, a middle box type solution, you can use Transit Gateway to push traffic through and back into the Transit Gateway for traffic that's moving across it. So really quite some cool capabilities there. Now, this is an advanced session, so there's a lot of kind of topics in here. So I wanted to give you a bit more of a detailed diagram of how Transit Gateway behaves. So normally we just show it as the single symbol with an attachment to a VPC, but here I wanted to show you a little bit more. So in red here, we have the Transit Gateway itself. Within that, we've created 2 routing domains, 2 route tables. We've got 4 VPCs across the top of the screen, and what you can see there are those network interfaces that we push into each availability zone that you're using for that particular VPC. So, what are our requirements here? If this is a regional service, the thing we want to do is centralize our VPN connectivity. So at the bottom of the screen here, we have our VPN connection back to our on-premises network. We want all 4 of our VPCs to be able to use it. In terms of scale, I'm showing 4. Remember, it can handle thousands. I couldn't fit that many on the slide, so we're going to go with 4 for now. But because we can cope with thousands of VPCs, that's potentially a lot of traffic. Those of you that have used the AWS site-to-site VPN service in the past, you might be aware that there's a bandwidth limit when you go to a virtual private gateway of 1.25 gig per second. Well, if you've got thousands of VPCs, there's a reasonable chance you need more bandwidth than 1 and a bit gig. So what you can do with VPNs here is you can create multiple VPN tunnels, and we'll then spread the traffic across them. So you could go up to maybe 40 gig over an IPsec VPN if you wanted to. And in terms of our requirements here, with these different network interfaces in each of the VPCs, what that means is we can actually be quite specific about how we want the traffic to route. So let's look at the rest of an example here. So let's go with a very simple one. We have Transit Gateway, we have a single routing domain, and we have our VPCs. Here's our first VPC. This is 10.1. We attach it to the Transit Gateway, and it is associated with this default routing domain. So we have a route now inside our Transit Gateway in the route table for that VPC, 10.1. Great, very easy. Of course, we need to put an entry in the route table in the VPC as well. And in this case, we know all of our VPCs are going to be within the 10/8 network. So we're going to put an entry in the VPC route table for 10/8 and send all of that traffic to the Transit Gateway. We then connect our second VPC. So this one is 10.2. Again, an entry goes into the route table inside the Transit Gateway, and we add the same 10/8 entry to that VPC's route table. We repeat this, 10.3, 10.4. What's the effect that we actually have here now at this point? Well, we have full connectivity between all of those VPCs. Just by attaching each one of them to the Transit Gateway, all 4 VPCs can now communicate with each other. So that's a single routing domain, a single route table. What about a slightly different requirement? We actually have the same 4 VPCs, but actually we don't want them to be able to communicate with each other. What we want them to do, though, is be able to use a VPN connection back to our on-premises network. So this is the consolidation design that I was talking about. So now we're going to have 2 routing domains. One is for the VPCs, one is for the VPN connectivity. We're still going to go and put an entry in the VPC's route table, but this time we're just going to put a 0/0 entry. So all traffic, just send it to the Transit Gateway. Inside the Transit Gateway, we're going to say, for that particular route table, send all traffic to the VPN attachment. So now we have a traffic flow from the top down to the VPN. Life is good. What about traffic coming back? Well, here we're going to create entries in the route table at the bottom here for the VPN routing domain, and this time we're going to say to get to 10.1, go via the first attachment. To get to 10.2, the second one, 3, and 4. But we've done this in 2 different routing domains. And what this means is that the routing domain for the VPC, it doesn't actually know how to get to any other VPC. All it knows about is the VPN connection. So what have we achieved at this point? Well, we can't get between VPCs. That was our goal. But we do have connectivity to our VPN connection. So now we've managed to share a single VPN connection or multiple VPN tunnels, if we need the scale, between all these VPCs, but we've blocked access between them. There is simply no route between them. So one kind of final design that I wanted to share with you on Transit Gateway was the concept of shared services. So here we have a development VPC, a testing, and a production. Now those 3 VPCs should never be able to communicate with each other, but they should all be able to use the shared VPC. Perhaps that's where you have your directory. Maybe it's where you have your logging, your monitoring. How would we configure that with the same setup? Well, once again, we can have the 2 route tables. We have 2 requirements here, and this is how we would configure them. We want no east-west connectivity. So in our VPC route table, we still say send all traffic for 10/8 down to the VPN. That's basically the same as last time. But we do have an entry here that says 10.4. That's shared services. That one we do have a route to. So now all 3 of these VPCs, they can reach the shared services, they can reach the VPN, but they cannot talk to each other. So all of this has just been done by having 2 route tables inside the Transit Gateway. And you can have multiple route tables for different routing domains, different configurations, depending on what you need. So if we take this a step further, what are we looking at from kind of a reference architecture point of view? What is the art of the possible? Well, you've already seen that we could have multiple VPCs and the shared services set up. That's kind of the standard that we have. We can then say, fine, we have even more accounts for doing things like authentication, cross-account IAM roles, the ability to connect into those accounts and consume their services. Of course, we're going to have Transit Gateway. That's the purpose of this part of the discussion. So we're going to connect these VPCs, all of them, to the Transit Gateway. Inside the Transit Gateway, we've put multiple route tables to identify the different behaviors that we want. And we're going to bring in connectivity using VPN. And within the next couple of months, Direct Connect will also be supported. Internet connectivity. That's probably quite important in most customers' architecture. So we could have a VPC where we put all of our outbound internet access. So perhaps we do some URL filtering, some proxying, NAT gateways. We can use Transit Gateway to send traffic for the internet to that VPC. For inbound, we might have perhaps some inbound inspection type appliances. Again, things that are presented to the internet, but then provide access to all of our other VPCs. Finally, we might have services that we want to put between different traffic flows. So IDS, IPS, again, you can use Transit Gateway to force that traffic into a VPC and then bring it back into another routing domain and onwards to its destination. So you kind of get the idea that Transit Gateway gives you a lot of capabilities here. So this enables all that connectivity between all of these different components, and equally, you can restrict it if you want to. Just to clarify a couple of things on the VPN side of things. So the Transit Gateway behaves in quite a similar way to the virtual private gateway. It is the termination point for your VPN connections. In terms of bandwidth, configuration, the APIs, it's the same as what you've done with your virtual private gateway, with one difference. It has the same 1.25 gig limit per tunnel, but this time you can add more tunnels to increase that bandwidth, as I mentioned. What does this provide? Well, technically, it gives you that encryption right the way to the edge of your VPCs. Transit Gateway doesn't sit outside your VPCs. It's actually part of each one of your VPCs. It has a network interface in all of them. So what this means is that your connectivity from on-premises, your encrypted connectivity, takes you right the way to the edge of your VPC, exactly the same as it did with virtual private gateway. More bandwidth, you add more tunnels. How does that actually work? Well, it uses something called ECMP, so equal cost multipathing. And what that means is the more tunnels you add, we will hash the traffic across them. And as long as your appliance on your end of the connection can do the same, you could get kind of up to 50 gig of connectivity easily over a VPN connection to Transit Gateway. You do need to check that your device and your configuration supports this. So some vendors' hardware only supports a maximum of 4 connections. Others support 10. So please check if you're going to use ECMP and multiple tunnels, what your hardware is actually capable of supporting. So I mentioned PrivateLink. One of the ways that you might choose to use PrivateLink, remember, is to present a service from a single VPC to other VPCs. Now, the way it works is it uses Network Load Balancer, which currently supports TCP. So as long as your application supports TCP and will work behind a Network Load Balancer, you can then expose it to all of your other VPCs. We've also got Transit Gateway, though, that allows you to talk between many VPCs. So why would you choose one over the other? So first of all, both of them support thousands of spoke VPCs. So scale is not a challenge here. But actually, there's a couple of key things. So you would use PrivateLink if you're sharing an individual application. If you want full network reachability, that's when you would use Transit Gateway. In terms of trust, you could use PrivateLink to share a service to any other AWS account. It only allows them to consume that particular service that you've published via the Network Load Balancer. Whereas with Transit Gateway, yes, you have routing domains, but actually it allows full traffic flow, so any ports, any protocols, and then you have to configure your security groups, obviously, to restrict that. So there is more trust involved in a Transit Gateway setup, but it does give you a centralized point of control. You can choose who can route to each other. In terms of dependencies, PrivateLink requires you to have Network Load Balancer and to have very specific application architectures using TCP, whereas with Transit Gateway, any traffic can flow. So that's kind of the balance between PrivateLink and Transit Gateway. So I'm going to take questions at the end, no problem on that, just so I can get through the rest of this content, if that's okay. So just going to talk about external connectivity. This is a diagram you might have seen before. This is the AWS Global Backbone. So this is the infrastructure that we have connecting our regions and our edge locations to each other, and back to the rest of the infrastructure that you're using within AWS. So it connects both the regions, the availability zones, and the points of presence for CloudFront, Route 53, and Global Accelerator. Now, this backbone obviously isn't made up of the single connections that are shown on the screen here. Each of these lines represents multiple 100 gig connections between each of these points of presence that we have. All of those are fully managed by AWS. This is our infrastructure, our network. So why do we have a backbone? Why do we have this in the first place? Well, first of all, from a security point of view, all traffic that is moving between our regions, with the exception of China, goes over the backbone. If you send traffic from one public IP address to another public IP address in 2 AWS regions, that traffic will go across our backbone. In terms of availability, we fully manage this infrastructure. So from that point of view, if there is maintenance happening on one of these circuits, we can take that out of service and make sure that you're not impacted by any sort of outage there. So we believe that we can ensure you have high availability for your connectivity by fully managing this backbone ourselves. Managing that availability also means that we can give you consistent performance. So from this perspective, we know the path that all of these packets are taking. We can give you the most optimal path available between 2 points on our network. And then finally, having the edge locations on the backbone means that we can give you the option to get onto our network sooner. So if you're using CloudFront, you enter our network at a CloudFront POP, you then go across our network, perhaps to the origin. And the same is true of Global Accelerator, which I'm going to be talking about in more detail in a moment. So as you might expect, multiple services use the AWS backbone. The kind of obvious one here is CloudFront, as I've mentioned, those POPs reaching over the network to reach their origin. Direct Connect. Direct Connect now enables you to reach any AWS region from any AWS Direct Connect location. So this private connectivity enables those paths from those Direct Connect locations to the regions, just with the exception of China. Inter-region peering. You can peer two VPCs in different regions with each other. When you create that peering connection in the console, what we actually do is we encrypt that traffic, and we then carry it across the AWS backbone between those two regions for you. That traffic never goes out onto the public internet. It stays on the AWS backbone. And then finally, Global Accelerator, which is the new feature I'm going to be talking about. That's another service that's consuming the backbone, and again, enabling you to jump onto our network sooner rather than later. Okay, so what is this Global Accelerator thing that I've mentioned a few times? So it gives you the ability to have a pair of IP addresses advertised from multiple of our CloudFront POPs around the world. So the same pair of IP addresses, we're going to announce them from multiple edge locations. I'm going to talk about it as a single IP address, but we give you two so that if you want to use two, you have the option. They go to different what we call network zones within the CloudFront POP. But for the rest of this session, I'm just going to talk about it as a single IP address to keep it simple. Each of those CloudFront POPs then has redundant and diverse connectivity back onto the backbone and to the rest of our regions. And when you access that IP address, that traffic is now taken into the CloudFront POP and then carried across our network. Instead of this being just for web applications or streaming media that is cached with CloudFront, you can actually target an elastic IP address with Global Accelerator. You can target a load balancer. So this doesn't have to be used for kind of standard cacheable web content. And actually, it's really quite easy to set up. So let's kind of look at the typical setup here for an application that you're hosting on AWS. You're sitting in your office, you're using your laptop, you're connected to Wi-Fi, and how it kind of works from your perspective is you access the application, it makes a connection to AWS, everything's good, yeah? The reality is a little bit different. What's happening, of course, is you're going through your internet service provider. You're then going through multiple other networks over the internet, subject to maybe internet weather events, a bit of packet loss here and there, a bit of variability. And actually, the path that your traffic takes could be different on the way to your application versus on the way back. So it's very unpredictable. You're going across multiple networks here. And Global Accelerator is intended to help mitigate some of that. So each one of those hops along the way could have a different impact on your traffic. So if you think about what our backbone enables you to do and gives you that availability and that consistency, what we've done here is made it so that you go out of your local ISP via the various peering arrangements that we have with all of our CloudFront POPs. You get straight into the edge of our network using that Global Accelerator IP address. Within Global Accelerator, we can then do some things like identify, do you have your application running in multiple regions? If you do, what is the closest region? And we can send your traffic there. If you only have it running in one region, but perhaps you have two entry points to your application, we can do a health check and see which one is available for you. But importantly, what we do from that particular edge location is we carry that traffic purely across the AWS backbone all the way to the region. So these IP addresses that I'm talking about, they're known as anycast addresses. So they're anycasted from all of our edge locations, which makes your application highly available and easily reachable from anywhere. So this is the example setup that I've been talking about. We have two different AWS regions. We have your application in it. I'm showing a network load balancer, but this can equally be an elastic IP address, as I've also put on the slide. We've got the CloudFront edge locations here. So this is where Global Accelerator is deployed. And we've created a Global Accelerator IP address, so 3.10.3.125. It doesn't just exist in that single CloudFront location. It's actually advertised from multiple CloudFront locations. So now when you make a connection to that IP address, as a user of this particular application, the connection comes in, and as I showed you on that previous diagram, forwards onto an AWS region. And here, because we have two regions, we've made a decision about which one we should send each user to. If for some reason you decide that you need to take down your application in one region, the health check will then fail, and we'll now carry that traffic across the backbone to the other region. So that's Global Accelerator, just a very brief tour of it. Let's just have another look at connectivity back to an on-premises environment. What's actually changed in this space? So connecting to on-premises, there's a couple of ways that you could do this. You could use the Virtual Private Gateway VPN, the one that's been around for quite a while. You could use Direct Connect. Direct Connect gives you 50 virtual interfaces on a dedicated port to connect to multiple VPCs. You could deploy your own EC2 instance to run a VPN service, no problem with that. And of course, you can use the new AWS Transit Gateway VPN. So all of these are good options for connectivity. But in terms of the ones that really scale really well, actually, it's kind of back to Direct Connect and Transit Gateway VPN. So Direct Connect, we can do 1 gig ports, we can do 10 gig ports, and we can do multiples of them. Transit Gateway, we've talked about the fact we can have multiple VPN connections. So let's just take a quick look at Direct Connect. In terms of what we did in 2018 with Direct Connect, there are a lot of new locations added, so 12 new Direct Connect locations, and 19 new Direct Connect partners. And our Direct Connect partners are key here because they're the ones who help you connect to our Direct Connect locations when you're not located within the same facilities that we are. So 19 new Direct Connect partners is great. In terms of increasing the performance for certain workloads, we enabled support for jumbo frames. So you can now get a 9001 MTU from on-premises all the way through to your VPC. And also, we launched a capability in some of our Direct Connect locations for logical redundancy. What this means is that you can have a physical connection, and over it run 2 separate BGP sessions for an individual virtual interface. What that means is if we do maintenance on one of our routers, you still have a path via the other one. It doesn't replace physical redundancy, but it does give you some options from a logical perspective. Also, we have the integration now with VMware on AWS. So if you're connecting to multiple VPCs with Direct Connect, the traditional way you would have done this is created a private virtual interface for each of your VPCs, each one going to its own virtual private gateway. For redundancy, you'd put in a second Direct Connect connection to another location, and again, you would send private virtual interfaces to each of your VPCs. If you wanted more bandwidth, the way you can achieve this, you can now use link aggregation. So you could have multiple 10 gig connections. So between your router and the AWS router, you could now have 4 10 gig connections, for example, 40 gigabits of connectivity. So at the moment, the default limit on that is 4 connections. If you need more than that, let us know. We can increase that limit for you. But we also went one step further. That link between a Direct Connect location and an individual region, that's no longer a hard link. Because what you can do is deploy a Direct Connect gateway. And Direct Connect gateway is a global object. So now when we create our private virtual interfaces, if we send them to a Direct Connect gateway, we can actually now attach up to 10 virtual private gateways in different regions to the same Direct Connect gateway. This means that you can consume Direct Connect from a location that is near to your data centers, to your premises, and then use our backbone to carry that traffic to the remote regions. Looking at how you might use that with Transit Gateway, so one thing you could do, of course, is use it in parallel. So using the older model, attaching to the virtual private gateway with virtual interfaces, that absolutely works fine. And that's currently what you would have to do if you want access directly into your VPC. The other way you could do it is use a public virtual interface to reach the VPN endpoints for Transit Gateway. So the way that works, when you have an AWS region and you create a public virtual interface over Direct Connect, it gives you access to all of the public IP addresses for all of our regions. Within those IP addresses are the endpoints for our VPN services, and that includes Transit Gateway. So if you want to use Transit Gateway today with VPN connectivity over Direct Connect, that's the model that you would use. In the next couple of months, we'll have native support for Direct Connect on Transit Gateway. So network services, let's just briefly talk about DNS. So from a DNS perspective, if you have your on-premises data center and you have a VPC, inside your VPC there is a DNS service. It lives on the .2 address in your VPC. However, if any of you have tried to configure perhaps an on-premises DNS server to reach that .2 address, that connection, it doesn't work. You cannot reach the .2 address from on-premises. Equally, from your VPC, if you wanted to be able to forward queries from your VPC back to on-premises, again, that's not a configuration that was supported. So what we saw customers doing here was deploying their own DNS server on an EC2 instance in the VPC, and then establishing connectivity between their on-premises and their VPC DNS server. So, okay, that's fine. You could do that. It connects then to the .2, but then how does this scale? If you have 3 VPCs, you have 3 DNS servers, you have more VPCs, that's even more DNS servers. So we launched a feature called Route 53 Resolver. What this enables you to do is present a network interface for inbound DNS queries inside your VPC. And this is reachable from on-premises. What this means is you could perhaps go from running 100 DNS forwarders down to one single endpoint. Now, of course, a single endpoint is not a good design. You're going to deploy multiple endpoints. So inside your VPC, you can choose multiple availability zones to put those network interfaces in. So you can also then create rules for forwarding. If you want to query your on-premises DNS using a certain set of names, you can create forwarding rules inside Route 53 Resolver, and then you can use Resource Access Manager to share those with multiple VPCs. They all use the same endpoints. So if you're doing a kind of large DNS setup at the moment, and this looked familiar to you, perhaps come and have a chat with one of us about Route 53 Resolver. Client VPN, getting towards the end here. Client VPN, we've talked about connectivity from a network to an AWS VPC. What if you have your users on their laptops who need to connect into AWS using a VPN? So client VPN uses OpenVPN clients. So quite simply, you have your VPC, you have your VPN endpoint that you create for client VPN, and you have your users. They use an OpenVPN-compatible client to connect to that endpoint. That's carried over the internet, encrypted using TLS. The client VPN endpoint then gives you access to the VPC. The VPC might have peering to another VPC. It might have access to the internet, other AWS services. But the point being that your users can benefit from anything that that VPC can already reach. So on-premises environments, you can use this VPN solution to come into a VPC and then back out to an on-premises environment as well. So from a multiple regions point of view, the only thing I just wanted to touch on here was I mentioned VPC peering earlier. We added a couple of other capabilities here. So support for DNS resolution, support for network load balancer, and PrivateLink. These were all things that we've added over the last year. So if previously you weren't using network load balancer or PrivateLink over peering, this is just a reminder that you can now do that. So just a couple of thoughts to wrap up the session. First of all, there are now lots of options you have, lots of tools, lots of capabilities to scale to many VPCs. But does that mean you should? That's a question for you. There's plenty of wiggle room, plenty of options here to choose the right solution for your particular use case. Spend some time with an AWS solutions architect, talk through what it is you're trying to achieve. Use the combination of services that I've talked about to meet both your scale requirements, but also your security requirements. We've touched on security a couple of times throughout the session. And finally, networking changes pretty fast. In a traditional environment, it doesn't. But in an AWS environment, we're continually adding capabilities and features to our networking. There are no more crystal balls here. If you can, start simple. Keep everything as simple as you can. It means that as we release new features, it's easier for you to integrate them and take advantage of them. And finally, segment your environment and then continually iterate. This is not a fixed setup. Just like your applications, the network design itself can evolve over time. Of course, make sure you're experimenting and testing these new features. So as we release one of these, go and build up a test environment. Give it a try. See how you might use it or whether you decide not to. That's the end of the session, a little bit over. If you've got some feedback, would really appreciate you using the QR code and letting me know. Thanks very much for your time.